Hello. Alrighty. Well, I'm going to be going through the practice physics test. The second two problems. It'll be similar to the problems on the test on Wednesday, and as per request, because we didn't have time in class to go over the problems, I'll be going over them now. Okay. So let's start with the second one. And once again, there's a chat. You can ask questions in the chat. You can access it by clicking in the description. Alrighty then. So I'll be watching it here, and so let me know if you have any questions. Okay, let's bring up the first problem that we will do. Here we go. Alrighty now. So let's make this bigger. Okay. Let's make this bigger. There we go. Alrighty. By the way, I apologize for any typos. Alright. So the first problem is a man throws a ball straight up past the edge of a vertical cliff 1,000 meters above the ground. The initial velocity of the throw is 20 meters per second upward. What time does the ball reach the highest point? How high does the ball go before reaching its highest point? At what time does the ball return to the position in which the man threw the ball initially? Alright, let's do those three first. Alrighty. So, I just want to say real quick a few things. Let's switch the screen here. It's not cooperating. Okay, there we go. Just want to say a few things first. Number one, remember the two formulas we use for motion, and remember the conditions under which they apply. All right, both of them apply in the case of constant acceleration. Number one, and number two, the distance formula applies in the form we have written when the initial velocity is 0. In our situation, the initial velocity is not 0. Okay, so we decide to pick a time in the trajectory when the velocity is 0 and go from there. Or we could use our final velocity as 0 just to get the time, and that'll work for part A. All right. So without further ado here, let's get going. Alrighty. I'm gonna make sure this everyone can see this. Good. All right. So let's get to it. I need to draw a sketch. Here's a guy. All right. He's chilling on the cliff. Oh, he's too high. He needs to get down. Get down. All right. All right, and here he is on the cliff. On the cliff. It's a big cliff. It's a legendary cliff. There we go. All right. How high it is doesn't matter right now. Ball going up at 20 meters per second. Here's a ball. It's a dodgeball. Goes up 20 meters per second this way. Okay. At some later time, it will get up to this high point where it will stop. And let me do one more thing. Let's take all this stuff and move it over a bit. There we go. There we go. He's living on the edge. So it'll get up to its highest point and stop. Then it will come back down to the bottom of the cliff. So let's just draw a little trail. And that comes back down this way, right? All the way down to the bottom. All the way down to the bottom. Okay. And the whole trajectory is supposed to be straight, but I moved it over from one side to the other just to exaggerate a bit. Alright then. Okay. So, part A, how long does it take to get to the highest point? Well, we know the change in velocity between 2 points in the trajectory is equal to negative gt if I call my positive direction up plus x. Okay. Now, G because we're in free fall, negative because the acceleration points in the negative x direction, right? So I'm going to call my delta V, remember, is just a change in velocity at 2 different times in the trajectory. So this is the velocity sometime. We'll call it V final minus V initial, right, is delta V. Okay. Okay. Let's call the final time. Let's label all the times in blue and red. Blue. When the ball is here, we'll call that T final for now. And when the ball is at the initial point, we'll call that time T initial. Alrighty then. So the change in velocity here is given by the velocity at the time T final, which we'll call V final. Okay, V final. And what is that? Well, it's the velocity at the final time T final, which is going to be 0 by definition of the top of its trajectory. Now, V initial is given to be 20, so delta V is 0 minus 20 meters per second, negative 20. Delta V is equal to negative G times the time it takes, let's say change in time. So T final minus T initial. That's what we're looking for, is delta T. So delta T, divide both sides of this equation, negative delta V over G, divided by negative G. It's equal to negative 20. And let's just round up to 10. Because we're lazy and we like easy numbers. Ah, you guys aren't lazy. I'm lazy. Okay? I'm lazy. So this is going to be equal to 2 seconds. Alright. Takes 2 seconds to get to the highest point. Bait. How high does the ball have to go? How high does the ball go? Well, when V initial is 0, which it's not, okay, and and acceleration is a constant, which is the same condition in the first part. The distance traveled, or the change in coordinate, is 1/2 times the acceleration times the time squared. And let's call that a change in time squared. So let's change our T initial and T final, shall we? We want our T initial now to be where V is 0. So I like this point, okay, and I like T final being here. Since the amount of time to go from initial, from where the red ball started to be thrown to T0 is the same amount of time to go from T0 down to the T final when it comes back down, right? So, okay, what we're going to write is the distance moved there. It's 1/2 G delta T squared. Now, I'm calling positive X down here because motion is downward, and I like my distances to be positive. Well, I like my distances to be positive. Who doesn't? Right? So we're going to put a G there. So actually this D is a change in coordinate, but we're going to shy away from changing coordinates right now and just point our positive X direction always in the direction of motion between our initial and final time. Okay. So D, which is what we're looking for, is 1/2 10 meters per second squared times 2 squared. It should all be in meters when it's all said and done. D is equal to 1/2. 2 squared is 2 times 10 is 20 meters. C. So C is, at what time does the ball return to its position at which the man threw the ball initially? Well, that time, my friends, is 2 times delta T. 2 times the amount of time to go half that trajectory from the initial throw to the top is 1 amount of time, and then getting from the top back down to T final here is double that time. So T is 2 times T, which is 2 times 2 seconds, which is equal to 4 seconds. C, D. Let's get our picture back. I'm tired of not working with it, to be honest. Let's bring it down. Copy. Let's paste it down here. Paste. There it is. Okay. Alrighty. So D is what is the velocity of the ball at this time. So at the time T, what's the velocity of the ball? Well, how do I say this? I can just write the change in velocity. Now let's let this be T initial here. I'm going to write my blue T initial here. Here, T final right on the other side of this. So exactly at the same height, right where you released it. Let's call that T final. Delta V between those 2 times it's going to be equal to negative G times the time it takes, which is 4 seconds. So 4, this is all going to be in meters per second when it's said and done. But let's write G as 10. 10 times 4 meters per second. Delta V is V at time final minus V at time initial, right? And the amount of time between those two is 4 seconds, so we are lining it up right. V final is what we're looking for. V initial is equal to 10 up. So let's call positive X up for now. We keep changing depending on the problem, depending on the way the wind blows. Well, that's the price we pay for using simple formulas. Alright, negative 10 times 4 is 4. Let me just write negative 40 here. Negative 40 meters per second. Alright, so V final is negative 40 plus, I'm sorry, this is not, is this right? Negative 40 plus 10. Sure. Negative 30 meters per second? This is not right. I don't agree with this answer right here. It should be 20 meters per second down. Answer should be negative 20. Not quite sure. I must have did some math wrong somewhere with maybe delta T. Doesn't look like it. 2 seconds to go up. 4 seconds for the round trip. V final minus 10. Oh, oops. The initial velocity is 20, not 10. 20 meters per second, right. Okay. V final minus 20 meters per second. So this will give us negative 20 meters per second, which is exactly right. The minus sign, remember, once again means that it's pointing in the negative x direction. Velocity is a vector. It has a direction and a magnitude. So that's minus 20. Alrighty. Goody goodies. Okay, now that makes sense. Part E. Part E. At what time, starting from the initial toss of the ball, does the ball hit the ground? 1,000 meters below the cliff. Okay. So this is 1,000 meters here. 1,000. 1,000. Now, we're looking at an instant right before the ball hits the ground. So ball when it's down here right before, so even closer than that, just before the collision, instant, a millisecond. Okay, so what we do know is, so this is what 1,000 meters, 1,000 meters. Okay, and what we do know is from here to here is this amount, 20 meters. And remember, to sum in this formula, d is 1/2 a delta t squared. We need to know that acceleration is constant, which it is in free fall, and that v initial is 0. So we need to pick t initial to be 0. So, sorry, t initial to be a time when the velocity is 0, which is going to be right here. And now our t final, well, it's the change in time, delta t. We want to correspond over when we travel a distance of this from t0 all the way to t final. It's 1,000 plus 20 meters, right? This picture is definitely not drawn to scale at all, but we get the idea. So that's 1,020 meters we're traveling, right? Okay, and let's call positive x down since that's our direction of motion in this problem. So that g is down, and that's going to be equal to 1/2 times 10 meters per second squared times the unknown time delta t squared. Okay, let's get rid of the units here. All right, so solving for this, we get 2,000. So 2,040 from multiplying 2 to both sides, and then by 10 delta t squared. So you get 204 is delta t squared. And so delta t is the square root of 204 seconds. Second squared here. Second squared, 204 seconds. Okay, gonna do a quick calculation. Square root of 204, let's see here. Square root of 204 is 14.2828 seconds. We'll say about 14.283 seconds. See the amount of time it takes to do what? No. Wait a second here. Let's see what time that corresponded to. The problem asks for starting from the initial toss, how long does it take the ball to get to the ground? Right. This is just the time from here all the way down to here. Okay? Just from the top of the trajectory to the bottom of the cliff. So now we got to add on that time from starting the part of the throw to the top of its trajectory, which we found in part A, 2 seconds. So let's add 2 seconds to this. Tack on 2 seconds, so the t total equals delta t plus 2 seconds, which is equal to 16.283 seconds. There we go. Alrighty now. Anything else? F. Part F. Okay, part F is, what is the speed of the ball at the tiny instant before it hits the ground? So what's the speed at the time t final? Alright? Well, let's keep the same t initial and t final. We'll have delta v there is equal to g, positive here, we'll just say 10, delta t. Alright. Do we know the amount of time it's going to take to get from top to bottom there is 14.83. Sorry, 14.283. And it's going to be all in meters per second. V final is what we're looking for. V initial, the velocity at t initial, which we have set right now to be at the top of the trajectory, so it's 0. So V final minus 0 is 142.83 meters per second. And we can just solve for V final by getting rid of that. There it is. Going pretty fast. Pretty fast. Alright. Okay. That is number 2 in the books. So let's get out of here. Let's get out of this. I hope I'm not making any mistakes because nobody's in the chat correcting me except for myself. And I think I've made no mistakes. Alright. Let's go to screens. There it is. Alright. 2 cars in different lanes heading in the opposite directions. On a 2-lane straight road, both cars are initially separated by a distance of 1,000 meters. One car is traveling at a constant velocity of 20 meters per second. The other car is initially at rest and is traveling with an unknown constant acceleration. Okay. Now when I say opposite directions, alright, what do I mean by that? Well, I would like them to meet each other at 400 meters from the starting point. So, according to part A, which means, this is number 3. Let's go ahead and throw it up on the screen. That means that basically you got to be heading towards each other, just in opposite directions, right? They're moving in opposite directions. Not this way, this way. Okay? Because they want to meet. Yeah, a picture would have been helpful. I agree. Test, probably going to have a lot more pictures in this practice test. All right. Here we go. Let's get it going. Number 3. Okay, so we got a car going this way. Some unknown A. V initial 0. We know what formula we can use for that. Now, separated from a distance that we're given is another car with a given velocity of 20 meters per second. It's constant. That's it for all times. Now they're separated by 1,000 meters initially. So let's write that. 1,000 meters. Okay. Let's call this guy, this is something that'll help you, car 1, and this guy car 2. Good strategy in a 2-object problem. Alright, so this is for car 1. Well, the distance traveled, which I want to be, well, I want them to meet 400 meters from the starting point, so find the unknown acceleration for that. 400 meters, I want them to travel in the time t. So let's say it's 1/2 unknown A times t squared. Car 2. I want him to travel, so I want him to meet 400 meters away. So this is in yellow, 400 meters, there to there. And then this, I'm going to put in light green, is going to be 600 meters. So I want this guy to travel 600 meters in the time t. That's going to be equal to, we're moving at a constant velocity, so the formula for that is just going to be the constant velocity v, so 20 meters per second times, it's going to be meters, times t, unknown t. Okay, so this will give me t, the amount of time it takes for them to meet, or where I want them to meet at 400 meters. It's going to take this much time for one car to get there. 600 over 20 seconds. Oh, which is going to be 60 over 2, so 30 seconds. All right. And now I plug t equal 30 seconds into equation for car 1. 400 is equal to 1/2 A 30 squared. Alrighty. To solve for A is equal to 2 times 400 over 30 squared, or 800 over 900, which is equal to 8/9 meter per second squared. Okay, so the acceleration must be 8/9 meter per second squared for them to meet 400 meters away from the starting point of the accelerating car. And you can read that in the directions. If you didn't follow that, please read the directions for this one closely. It should make sense. So not very fast. Slower than gravity. So it's moving pretty dang slow. Okay, so, but it did start from rest, I guess. All right. So, part B. How far apart are the cars from each other at 5 seconds after the initial time? So what we want to do is take the change in coordinate from the two. So whatever that means, right? Delta D, change in coordinate. So I'm going to take 1/2 or t equal to, hold on, so t equal to 5 seconds. So this here was 30 seconds. Okay. So we're going to take this car's function for distance, right? 20 meters per second times that time minus this one. All right. So we're going to get 20 meters per second. Sorry. 20 meters per second times the time of, well, it says, sorry, 5 seconds. So 5 seconds times 5 seconds minus 1/2 8/9 meters per second squared times time of 5 seconds squared. Just going to get me with meters here. So the change in distance there is going to be what? 20 times 5 is 100 meters minus 25 over 2 times 8/9. Oh, your guess is as good as mine. 12/5 times 8/9. 12/5 times 8/9 meters. Gonna plug that into a calculator. All right, let's see here. 100 minus 12 divided by 5 times 8 divided by 9. 97. There's still going to be 97.866, sorry, meters apart. Is that right? So check. Car 1 has moved 100 meters. Car 2 has moved 12/5 times 8/9 meters. Whatever that is. Let me look. Sorry. 12/5 times 8/9 is 12/5 times 8/9 is 2.133. Jeez, that's slow. Is that for real? I think I switched it. This guy's moved 100. This guy's moved 12.833. This is the slow mover here, meters. And yeah, what I want is this distance here. So that's not quite what I have there. All right. What I have there is delta D, which is in blue. Delta D is the difference of those two, when really I needed the sum to get the part in red. So I need to get the part in red. I get that by adding those two together, right? Not by taking the difference. And that gives me, let's see here, 100. Let me redo this calculation. Put a plus 102.133 meters. Okay? And now what I do is I say the part in the red plus the part in the blue, which is what I'm interested in, right? Is equal to 1,000 meters, right? So we got delta D, and then let's put a plus here. We don't know what it's going to be, and that's equal to, it's what we're looking for, plus the difference between the two, called D sub B for D between, must be equal to 1,000. So 1,000 minus delta D equal to dB. So dB, the distance between them, is 1,000 meters minus 102.133. Is it 1,000 or 100? Part, yeah, 1,000 meters initially, right? dB is 9. Let's see here. 900. No, 800. Sorry. 897.966. No. 866 meters. Let me verify that. Sorry, my head slipped. 1,000 minus 102.133. All right, 866,867, same old difference. Okay. This was actually repeating, so that's why I put 66. All right. Good. Alrighty then. And that is the distance between them. Now it's a lot easier when you're using x coordinates just to subtract the coordinates at that time, but we're not using coordinate systems, so excuse me for the awkwardness in solving the problem. Alright. Alrighty, so E, what is the average velocity of the accelerating car between t equal to 3 seconds and t equal to 10? Also, what is the average velocity of the car between t equal to 5 and t equal to 20? So the accelerating car, remember average velocity, V average, between the two times is velocity at the time of 10 seconds velocity at the time of 3 seconds, divided by the change in time. All right? So the change in time is going to be 10 minus 3, which is 7 seconds. The change in position, sorry, it's the change in position over the change in time. Let's see here. T equal to 3. So the distance traveled at t equal to 3 minus the distance traveled at. So it's going to be 1/2, 8/9, and then t equal to 10, 10 squared, minus 1/2, 8/9, t equal to 3 squared, which is equal to 1/2, 8,917. 100 minus 9 is 91 meters per second. And nothing looks great about that. Let's go ahead and plug it into the calculator. One half times 8/9 times 17 times 91 is 5.77 meters per second. Okay. Now I also want the V average between 5 and 20. So we're just doing the same things, plugging in 5 and 20 instead of a 10 and 3, and then the change in time is going to be 5 and 20. So 20 minus 5 is 15 seconds. So let's just write 1 over 15 seconds here. Then we'll get 1/2 times 8 9 in both terms, so 1/2 A in both terms, and then 20 squared minus 5 squared. Okay. So what do we get? Well, we're going to get 1 over 15, 4/9, taking the 2, 8 over 2 to get 4. 400 minus 25 is 375. And what does that equal to? Let me type it in. 375 times 4 over 9 times 1 over 15. And it's 11.11 meters per second. Okay. Alrighty, part D says, what time will the car that's initially at rest reach the same speed as the other car? So what time will the car that's initially at rest reach the speed of 20 meters per second? So let's use delta V, A delta T. So we're solving for the amount of time it takes to get a change in speed of 20 meters per second. So you know this is 8/9. You know this is 20, and this is going to be, sorry, mistake. Reverse it. 20, 8/9. This is going to be in seconds. This is going to be 9 times 20, which is 180 over 8 seconds, which is going to be equal to 180 over 8 is, let's see here. You never have to simplify these things. I just do it, see if we get the same answers. 22.5 seconds. E. Okay. Oh. Oops, this was part E. And this was part D. And I think I skipped part C. Yeah, I skipped part C. Sorry about that. Let's just do it down here. C. At what time will the car moving at a constant velocity reach the position of the other car? So at what time will the car at the initial velocity of 20 have moved 1,000 meters, right? So we have D for that, which is going to be the distance moved is just the velocity times the time. So time is just going to be distance over velocity. This is for a constant velocity. Okay. All right, so this is 1,000 meters divided by 20 meters per second. Just going to be equal 1,000 over 20 is 50 seconds. Okay, so I did E, D, E, C. Okay, in a weird order. All right. So we did E, we're on F. Sketch the graph of the position and velocity functions of time for each car. Comment on the mean and slope for each graph. Should be a total of 4 graphs. Great. Okay. So for car 1, we had position as a function of time. So let's say what we're talking about here. 1/2. Now let's just plot the distance traveled. 1/2 AT squared is the form of it, and that's all we care about. So here we go. T, here's D. It's going to look like some quadratic starting at D equal to 0, meaning I traveled 0 distance in 0 time. So comment here is that the slope of the graph is always changing. Slope is always changing because it's speeding up. Because it is speeding up. That's for car 1, and the velocity is a function of time. It's going to look like what? Well, what formula do we have? We have the change in velocity, or just the velocity at any time. Since the initial velocity is 0, it's just going to be a times t. So here we have increasing velocity linearly. Here's v, here's t. And we're going to say the slope is a. Slope of this graph is a. See, v versus t, the slope is a. The acceleration. 9/8 meters per second squared. Now the other guy, the distance he traveled as a function of time, it's going to just be v times delta t, v times t, letting t initial be 0. Here we go. D, t, this is for car 2. Alright. We just got a constant line here. Slope is v, and it's constant because we're moving at a constant velocity. Velocity as a function of time is just v, right? V, t, here we go. Always stays v. Slope is 0 because velocity is constant. Alrighty. Whew. Alrighty. So let me check the chat real quick, see if anyone's asked the question. I think that would be an adequate amount of time to take a test. Alright. An adequate test length. So good luck studying. Hopefully it all makes sense. Leave a comment if I made a mistake. Probably did. Okay. Especially with no one here checking my work. So peace out. Have a good night. And good luck studying for the exam. Bye.